Hi friends, welcome back to Eripedia World. Last lecture we started discussion on electromagnetism and we saw Orsted's experiment, how magnetic field is created by a current carrying wire, and we also discussed shortly the right hand thumb rule. Today we will take our discussion further from the point where we left and we'll see how the magnetic field is created in a current carrying loop. What is the behavior of magnetic field in such a scenario? And then next we'll see what is the nature of magnetic field generated by a solenoid. A solenoid is basically a cylinder coil which is carrying current. So these two discussion will be a continuation of our initial discussion from the last lecture. Let's start with the current carrying loop. Next, let us discuss about the magnetic field due to current in a loop. Here we have a circular loop which is carrying current, and the arrangement is such that this end is attached to the positive terminal and this end is attached to the negative terminal, so that current is flowing in clockwise direction in this sense. So this is my direction of current flow. Okay. Now, given this is the direction of current flow, what will be the magnetic field generated due to this current carrying loop? In order to see that, let us treat a particular part of it. Let's imagine we are at this segment of the current carrying loop. So here what you observe is that the current is, if I take that segment out, that can be approximated as a straight section if it is very small, and the current here is going in the upward direction. Therefore, by the right hand thumb rule, what we can say is thumb is pointing upwards and the curl will be in this direction. Okay. Therefore, the direction of magnetic field at this segment is in anti-clockwise direction if seen from top, right? Now similarly, every small segment will have similar behavior of the magnetic field. Here also there will be magnetic field in the vertical direction like this. Okay, and now if we come to this part of the segment, we will have a smaller segment similar to this, but the only difference is the current is flowing in the downward direction. And since the current is flowing in the downward direction at this part of this current carrying segment, we'll use the right hand thumb rule, and that will give me the direction of magnetic field in this direction, that is clockwise when seen from the top. Okay, so the forces of magnetic lines of force will be anti-clockwise as seen from the top in this segment and clockwise as seen from the top in this segment, right? Therefore, the magnetic fields will be nearly concentric, very close to the current carrying wire here. Also, the magnetic field will be concentric, very close to the current carrying wire here, and the direction of magnetic field will be opposite in both the segments. Therefore, at the center, this segment, this part of the current carrying loop will produce a magnetic field in this direction, and this will produce a magnetic field in this direction. So both the sections actually produce the magnetic field in the same direction at the center, isn't it? And what we can see from this is that at the center, the magnetic field due to this portion and this portion will add up, and it will be a straight magnetic field line in this direction. But close to the current carrying wire, the magnetic field will be concentric. So what we can say from this is that the nature of the magnetic field lines will be concentric close to the wire, and as we move away from the wire towards the center of the loop, it will become straight. Okay. Now once we understand the nature of the current carrying lines, magnetic lines, let us see how the magnitude of the magnetic field developed can be increased. One, as you might have thought out yourself, is if we increase the amount of current flowing through the loop, then the magnetic field will increase, because the magnetic field is kind of generated due to the current carrying field wire, and given that it is generated due to the current carrying wire, more the current, more will the magnetic field. A second way to increase the amount of magnetic field is by increasing the number of loops. Let's say we have one loop and it produces a certain magnetic field. If we make it 5 loops, then the magnetic field generated will be more. Why so? Because the same current is flowing through all the loops, and as a result the effective current is increasing. That results in an increased magnetic field. Okay, and also we can say that the magnetic field lines are denser close to the wire and rarer or less dense spread out away from the wire. Right? Now let us see the nature of the magnetic field, as in how does this loop behave as a magnet. If you observe that, then you will see that the magnetic field lines are going from this direction to this direction. Therefore, this end, the end facing out of the paper, will be the south pole of the equivalent magnet, and inside the paper will be the north pole. So we can basically replace this whole system by a bar magnet which has the south pole here and the north pole here, because then my magnetic field lines will be like this, and then outside it is like this. Therefore it is parallel to my current carrying loop. Okay, and as a result this system can be thought out as a dipole or as a magnetic bar. Now in order to decide that this is the south pole and this is the north pole, there is a rule which is known as the clock rule. We can use the clock rule to decide which is the south pole and which is the equivalent north pole. The clock rule says, let me write it here, clock rule. Suppose you have the loop. Okay, this is my loop. So basically the current is flowing in anti-clockwise direction seen from outside, and in that case, if the current flowing through the loop is in anti-clockwise direction, then this face is my north. The outside is north. The direction from where you are seeing is north. On the other hand, if the current flowing is in clockwise direction like this, since this is positive and this is negative, then the direction from where you are seeing, that is the south. Okay, so as in this case, if you observe, since the current is flowing in the clockwise direction, from where you are observing, that is the south, and the other end will be the north. So this is my clock rule. This decides what polarity will be which end for the magnetic loop. Okay, if similarly here, if we change that polarity, then this would have become the north and this would have become the south pole. Now that we have seen the nature of magnetic field produced by a loop, next let us see the nature of a magnetic field produced by a cylindrical coil, or what is known as solenoid. Now let us see the magnetic field produced due to a solenoid. So to begin with, let me tell you what exactly a solenoid is. A solenoid is basically a cylindrical shaped current carrying wire. So you can think of it as the shape of a helical spring. So a current starts flowing from here and it passes through all these loops and finally it goes out from here. Now what happens here is that each loop is similar to the loop here, just that it is also traversing a little in the depth direction, but it is similar to a loop system. Therefore the current carrying wire should produce a magnetic field. Now how does the magnetic field nature behave? See, the current is going from here. If you observe from this direction, then the current is going in clockwise direction here, isn't it? If you observe from here, then the current is in clockwise direction. Therefore this end will be my south pole, and if you observe from this end, then the current is in anti-clockwise direction. Therefore this is my north pole. Now we have decided our polarity for the magnetic field. Okay, now each of this loop will produce a magnetic field of its own, right? And they will kind of add up. As a result, inside the solenoid, the magnetic field lines will be parallel to each other and parallel to the central axis. So they will be like this. But as soon as we come out of the solenoid, since there are no more loops, they will start to deviate away from the central line. Fine. And to close the circuit, or to close the magnetic loop, basically inside the solenoid, the magnetic lines is going from south to north, and outside it is from north to south, thereby completing the magnetic lines. Always remember that the magnetic lines cannot break in the middle. It has to complete itself. Fine. So this is the basic structure of the magnetic field due to a solenoid. Now how can we increase the magnetic field? One, the very easy method is to increase the current. Second is to increase the number of loops in the solenoid. So these two things can increase the magnetic field. Fine. The magnetic field can also be increased by placing a soft iron core here. What happens is, if you place a soft iron core here, iron has a high magnetic permeability, and that results in an increase in the magnetic strength. Now, as we have already discussed, this behaves as the south pole and this as the north pole. And you can see that this case is much more parallel to a bar magnet compared to the first case here. This was a single loop and it was not really a bar magnet parallel, because inside it was highly circular, whereas in bar magnet these are supposed to be straight line. But this I presented just to give you a brief insight about how the magnetic field lines behave. But here, if you see, the behavior is almost exactly same as the bar magnet. So instead of this, we can place a bar magnet with this as the south pole and this as the north pole, and that will result in magnetic field inside the magnet from south to north and outside the magnet from north to south, very similar to the nature which we are observing here. Therefore, the magnetic field due to a solenoid is very parallel to the magnetic field due to a bar magnet. Now, what are the similarities and the differences between the two cases? The first similarity is that the nature of the magnetic field is almost the same. Second thing is, if this solenoid is suspended freely, then this will start pointing towards the north-south direction of the Earth's magnetic field, similar to a bar magnet. And also this solenoid, due to the creation of north-south poles, starts possessing attractive and repulsive behavior. So if I bring a bar magnet close to the north pole here, it will attract. If I take the north pole and bring it close, they will repel. So it starts behaving in that sense close to what a bar magnet behaves. But there are some differences too. One of the basic difference is, in a bar magnet you cannot really change the strength of the bar magnet. Here you can easily change the strength by either changing the current or changing the number of loops, right? Second is the direction of the bar magnet. You can reverse by reversing the direction of the current. Now suppose the current starts flowing in this direction, then my north and south will just reverse. We do not have a parallel concept in the bar magnet. That is, you cannot change the polarity just by changing something. So this gives you an idea about the magnetic field created due to a solenoid. And initial part of the lecture we saw the magnetic field created due to a current flow. And this will bring a close to today's lecture. Next lecture we will see the discussion on electromagnets, and also we will see some idea about what a permanent magnet is. Then we will see certain uses of a electromagnet. Till the next class, have a great day. Goodbye.